This is lecture 6 for week 12 of CS 1030. In this lecture segment, we're going to talk about control flow. And so this is sort of a significant step forward in the kind of complexity that we're going to deal with in our programs. So far, our machine language and our assembly language programs have run from top to bottom. That is to say, they start at address 0, then they load from address 1, and then 2, and then 3, and eventually they reach a halt instruction and they stop. It turns out that there are a lot of kinds of programming problems that we'd like to solve that are very hard to solve with programs that fit into that paradigm. So for example, if we want to do something like blur an image, we would need to have separate instructions blurring each separate pixel of the image. And so if our image had a couple of million pixels, we'd have to have a couple of million lines of assembly language to do the blurring. So that just doesn't really work. It's not a good idea. It's not a good use of machine resources. So the next thing we're going to look at is adding branching and conditional logic to our assembly language. And this lets us do things like loops and if statements in our assembly language. And if you remember those from scratch, in assembly language, they're basically going to be the same thing. So what we call this is control flow, since the program is now controlling the flow of its own execution. And this makes the assembly language much, much more powerful, but it also makes it quite a bit more complicated to write and quite a bit more complicated to debug. So we're going to now have to start paying quite a lot closer attention to how our programs are structured if we want to make everything work. So the control flow instructions in our assembly language, there's going to be several of them, and we're going to start with the simplest one, which is the jump instruction. So what jump does is changes the program counter to a new value. So it loads a fresh value into the program counter. And when the program counter has a fresh value in it, it's going to load the next instruction from somewhere else, from that fresh value. And so execution is going to jump to somewhere else in the program. So that's why it's called jump. So let's look at a program. So here we're loading from address A into R0. So we're going to load 1 into R0 since A holds 1 here. So here's a label R. So R, of course, doesn't generate any instructions. It's just a label. And so the next instruction is going to add R0 to R0 and put the result in R0. So what does adding R0 to R0 give us? It gives us 2. So this instruction doubles whatever's in R0. Now we're going to jump to R. So what does this do? This turns into a jump instruction, and the destination of the jump is the label R. So remember that labels simply refer to memory addresses. So what this is going to do is take the address specified by R, which is the address of this add instruction, load it into the program counter. So now after the simple computer finishes executing the jump instruction, the next instruction executes is not the halt, but it's rather the add. And so now it's going to add whatever is in R0 to itself again. So it's 2. So 2 and 2 gets added together. And so now we get 4 in R0. And it's going to keep going. So it's going to go 8, 16, 32, and eventually pretty soon it'll overflow. So this program uses control flow. It's not a very good program because it never reaches the halt. This is an infinite loop. The program loops forever. It just keeps overflowing R0. So it's not a very good program, but it does illustrate control flow. So next, we're going to look at a more interesting control flow construct, which lets us avoid this kind of infinite loop. And so this is more complicated. So this is a conditional jump. It's like a jump, but the jump only executes sometimes. The jump only executes if certain conditions are true. And so let's look at how that works. So the way the conditional jump works is we're going to do it's going to pair with a comparison instruction. And so this is sort of legitimately tricky. So let's sort of skip over our program except for the comparison instruction here. So when we get to this instruction, we're going to compare the contents of register 1 with the contents of register 0. And the way that works is the processor, the simple computer, executes the compare instruction, and it kind of remembers the result of the comparison. So that gets stored in a special register. And if you want to, you can dig into SC4 and find where it's stored, but we're not going to bother with that for now. So the result of the comparison gets saved in the CPU somewhere. And now we have a conditional jump instruction. So BGT stands for branch if greater than. So what's going to happen is if R1 was greater than R0 at the time that the compare instruction executed, then the BGT is going to jump to R. Otherwise, it's not going to jump. It's just going to fall through normally to the subsequent instruction. So what's the program going to do? What the program's going to do is, like the previous program, it's going to keep doubling the contents of R0, which starts out at 1. It's going to double it, so it's going to go 2 is going to be here. Now, the question is, we're comparing R1, which was initialized to 20, with R0. So the question was, is R1 greater than R0? So if 20 is greater than 2, then we're gonna branch to R. So now R0 becomes 4. We're gonna compare 20 to 4. 20 is still greater than 4. So the branch greater than fires again, and we go back here. Then it goes 8, 16. And finally, when R0 contains 32, we're gonna compare 20 and 32. And 20 is not greater than 32. So we're not gonna branch to R. Instead, we're gonna halt the program. So what this does is it gives us a way to branch to a different location in a program only if something was true. And what you want to do when you're writing code is always pair a conditional branch with a compare. There's no real sense having a conditional branch without an immediately preceding comparison instruction. It's just not something you should do. It doesn't make sense. And again, you can trust the processor, the simple computer, to remember the result of the comparison in between the two, in between the compare instruction and the following branch. And the reason that's split into two is it makes each individual instruction simpler. It has to do less work, and it sort of makes the design of the computer easier, even though it makes programming the computer harder. So there are two conditional instructions, or two conditional jump instructions in the simple computer 4. There's BGT, which we used in this program, and there's also BNE, branch if not equal. So let's look at how to use these. So here's some pseudocode. So we're going to read in a value x. If x is less than 0, we'll negate x, and then we'll display x. So what's this going to do? It's always going to display a non-negative number, because if x had been negative, it will be flipped, it'll be inverted. If x was positive, the conditional code doesn't run, and we'll display the positive number. So what we're going to do now is look at how to do this in assembly. So here it is. So let's talk about this a little bit. So the simple computer doesn't have an input instruction. It doesn't really have like a keyboard or a mouse or any other I/O. So instead of the input, we're going to sort of simulate that by loading from memory. So we're going to load a value from location A, from label A. So we're going to load 4 into R0 here. So that's our input. Now we're going to clear R1. And why are we clearing R1? Well, there wasn't really anything over here that said clear R1. We're doing that as part of having decomposed the problem into simpler parts. We just sort of need to have a 0 in R1. And the reason we need a 0 in R1 is because we're comparing x with 0 here, and the comparison instruction only allows us to compare register values. So this is sort of the reason. So there wasn't anything in our pseudocode that said clear R1. We're doing that because that's what we need to do to make the high-level program work. Okay, so now we're going to compare R0 and R1. And here's something tricky now. Here's something you're going to have to sort of really pay attention to when you write your own programs. So we're going to do branch greater than done. But here's the thing. The comparison wasn't a greater than, it was less than or equal. And so what's going on here? We have to be super, super, super careful. So what's going on is the greater than condition is the exact opposite of the less than or equal to condition. Okay, so for any two numbers, if we want to check if one of them is greater than or equal to, we can compare if the other one is greater than, and then we can just flip that flag. So what we're doing is, if we do the branch, we're branching to the unconditional code. We're branching to the around the conditional code. And then we're executing the conditional code only if we didn't branch. So if x is greater than 0, we branch. So we only execute the conditional code, which corresponds to this, if x was less than or equal to 0. So what's that? So it's just basically a little bit of mental flipping around of things in order to get what we need done in the assembly language, get the thing specified in the pseudocode done using the operations that we actually have available in the assembly language. And like I say, this isn't particularly easy to put all these elements together at once. We're going to go through another example in even more detail after this, but we sort of have to get used to decomposing these more complicated high-level operations from the pseudocode into the incredibly simple things that SC4 can actually do. Okay, so the conditional code here that we branched around, if the greater than condition was true, just subtracts R0 from R1. And so let's look at what's going on here. Well, R1 we already cleared. So R1 contains 0, and 0 minus whatever's in R0, and put that in R0, that negates X and puts the result back into X. So R0 in our machine language program, or our assembly language program, was currently holding the value of X. Okay, so now we're back in unconditional code. Here we're back in code that executes regardless of whether the if branch executed. We're going to store whatever in R0, so store X into a variable called display. And again, our simple computer doesn't have a screen or something, so we can't actually display it. So we're going to pretend to display it by storing the value into a variable called display, into a memory location called display, I should say. Okay, so I hope that was clear. There's kind of a lot going on here. We're going to go through another example right now that hopefully will make this even more clear. Okay, so we have another piece of pseudocode. We're going to input X. If X is less than or equal to 5, we're going to multiply X times 2. Otherwise, we'll negate X. And then whichever branch we took, we're going to display X. So display X is not conditional. So we have an if then else. And so what we're going to look at now is how to convert an if then else construct into assembly. So let's sort of start breaking this down. So again, we don't have IO devices on our simple computer. So all we're going to do to input X is load A. So A is holding X into R0. So that takes care of the first statement. Now the second statement is going to take several machine language instructions. So the first thing we're going to do is load B into R1. And B is how we're getting the value 5. And so here's something tricky that I want to take a little bit of time to try to explain properly. A and B look the same in computer memory, but B is really kind of part of the program. B is kind of hard-coded in a program, and the value of A is our input. So they look the same in memory, but they're serving different roles. And that's just something we have to get used to when we're doing this kind of programming. Okay, so now we have the values that we want to compare in R0 and R1. So we'll execute the compare instruction on them. And again, we're going to see sort of the same trick. So if X is less than or equal to 5, we want to do something. So what we're going to say is, if X is greater than 5, we're going to go to the else part. So E is going to be a label for the else part. We haven't filled it in yet, but it'll be there in a second. So if X is not greater than 5, then it had to be less than or equal to 5. So then we're going to execute the then part right here next. And so let's look at that. So the then part adds R0 to R0. So that's the same as multiplying times 2. We don't have a multiply instruction on the computer, so we can't multiply R0 times R1 without a multiply instruction or some more complicated code, but we can multiply by 2 just by adding it to itself. So we're going to multiply by 2 by adding R0 to itself and storing the result into R0. And now that we've done the conditional code, we're going to jump around the else code to the unconditional code following the loop. Okay, so now we're done with this part. We're done with the sort of green part here. So now let's look at the else branch. So we jump to this case, we jump to label E if X is greater than 5, which is exactly true when X fails to be less than or equal to 5. And here we're going to clear R1, and we have to understand what's going on here. So why did we load 0 into R1? Well, we did it because we don't have a negate instruction on the simple computer. We don't have a negate instruction, but what we can do is we can take 0, and from 0, we can subtract X and store the result into R0. And if we take 0 minus X, that's the same thing as negating X. So we're negating X and storing the result into overwriting X with the negated value of its version of itself. And now we're done with the else part. And so we don't need a jump here. We don't need a branch or a jump to get out of the else part, because we're just going to fall through to the next instruction anyway. So there's 2 ways we could have gotten to the store instruction here at F. We could have either fallen through from the subtract if we executed the else part, or we could have jumped here with an unconditional jump from the end of the then part of the conditional. So again, there's kind of a lot going on here. It's fairly complicated stuff in the sense that there's, the individual parts here are pretty easy, but there's just kind of a lot of moving parts. And if you get any of them wrong, your code won't really work. So this is sort of stuff where you really need to kind of study these notes and try out a bunch of stuff in the simple computer before you can get it to work. Okay, so then our last thing we want to do is display X, and we can't display X because we don't have IO devices, so we're just going to store it again to a variable called display, and now we're done. Okay, so conditionals and loops in assembly take some getting used to. We haven't looked at loops yet, but we will in the next lecture segment. This is fairly hard stuff, and we're going to give you plenty of practice.